Welcome back to this channel. In this video, we're still in the subtopic 3.1 galvanic cell, at where in the previous video we still have two learning objectives haven't covered yet. The first one is the meaning of the standard electrode potential. And then the last one, which is the E, is stated the half equation and also overall equation. So, and then we will also cover the cell notation as we mentioned previously. And then please remember that we need to include the phase and also concentration when you're writing the cell notation. And then we need to know what's the meaning of standard reduction potential, standard cell potential. Okay, so one is cell potential, one is electrode potential. So what's the difference? And then we're able to understand the meaning of SHE. And then we will going to construct the series. Then we will going to compare the strength of the reducing and oxidizing agent. We calculate the standard cell potential and then also spontaneity of a redox reaction. Okay, let's start with the cell notation. In the previous video, we have roughly mentioned cell notation is as easy as ABC, which represent anode, salt bridge, and also cathode. Okay, anode always is at the left hand side, while these two lines is represent the salt bridge. Okay, and then right hand side is represent the reaction happen at the cathode, which basically is the reduction, and at the left hand side is the oxidation. As just now in the learning objective say that we have to state the physical state and also the concentration. So physical state solid, so no need to highlight the concentration. Aqueous, yes, we need to give the concentration. Aqueous also the same solid. Okay, so as we know that from here, just now we say that the left hand side is represent the reaction happen at the anode, and then anode always undergo oxidation. So that's why you will notice that the zinc will produce zinc 2 plus by losing 2 electrons. Next one, right hand side is the cathode, so which will undergo reduction, at where you will notice that CO2 plus gain 2 electrons to form copper. So then by this combining these two half equation, we will have the overall equation, at where we can say that the electron that lose by the zinc will gain by the CO2 plus. So at different side, it can be cancel out each other. Another things that we need to highlight over here is you will notice that this is the salt bridge. When you draw the cell diagram for the galvanic cell, you will notice that the salt bridge is immersed into the solution. So you will notice that both left and right hand side, exactly left and right hand side of the salt bridge will be the aqueous solution. Okay, let's look at the exercise. For the cell below, so write the reaction at anode, cathode, and also overall equation. So as like a previous example, anode is happening at the left hand side, so it's zinc lose 2 electron and then produce zinc 2 plus equals plus 2 electron. Okay, while for the cathode will be the Cr3 plus aqueous, and then gain 3 more of electron to form chromium. So when you want to write the overall order of reaction, you will notice that the number of electron cannot be cancelled out totally. So that's why in this equation, for the anode, you're going to multiply with 3, and then the cathode you need to multiply with 2, so that the number of electrons can be cancelled out, which is 6 and 6. So this one will be 2 more, and then this is 3 and 3. So end up the overall order of reaction will be 3 mole of zinc react with 2 mole of chromium 3 plus, going to produce 3 mole of zinc 2 plus and 2 mole of chromium solid. Okay, so I think I missed out the solid over here. Next part of the question, which is the magnesium. Again, we know that magnesium will going to, we need to write down and not cathode because the question didn't mention. Okay, anode is the magnesium solid, and then we'll produce Mg2 plus aqueous plus 2 electron. While for the cathode will be the Sn4 plus aqueous, and then gain 2 more electrons to form Sn2 plus aqueous. So the platinum over here actually is we call inert electrode. Inert electrode basically is means they are not involved in reaction. Okay, we need this electrode because we need to connect the wire with the voltmeter. Okay, so with this we can ignore the platinum in the half equation and also overall equation. So now we combine this equation. Since for this case 2 more electrons at both different sides, so we can totally cancel out that. End up we will have 1 more magnesium react with 1 more Sn4 plus, will produce 1 more magnesium 2 plus and Sn2 plus. Okay, proceed to next exercise. Construct the cell diagram. Another term for cell diagram basically is cell notation. And then as we know, in the previous slide, we always mention cell notation is as simple as ABC, where the A is represent the anode, and then it will undergo oxidation. So based on the overall equation given in the A, we need to identify the species undergo oxidation. In this case, we notice is Pb to Pb2 plus. So let's start with writing the cell notation. So we start from the Pb solid, and then this line basically is represent phase boundary, because next I am going to write the Pb2 plus, which is at the aqueous form. Don't forget, just now we have mentioned, besides mention the physical state, we also have to put the concentration. Okay, as this is just direct simple exercise, so it is not mentioned the concentration, so you can put X molar, and then followed by the short bridge, which is 2 straight line, and then with bromine Br2 aqueous. Then you will notice that Br negative also is in the same phase. So aqueous, aqueous. So if this case happen because they have same phase, we are not going to use the straight line because the straight line is represent phase boundary. So at here we will use the comma Br negative aqueous, and then also with X molar. Okay, this one here also similar case. Okay, miss out this X molar, and then we have to put comma because they are in the same phase. And then again, when you imagine back the cell diagram, the galvanic cell, so no matter both cathode and anode must be the electrode. So in this case, we are going to continue with the phase boundary, and then connected by the platinum, which is in the solid form, which this one is represent inert electron. Okay, now we're going to do question B. So when we look at question B, you will notice that the species undergo reduction is AU3 plus to AU. Okay, this one is undergo reduction. So in other words, to say MnO4 O4 negative is undergo oxidation. So we're going to start with MnO4 2 negative aqueous X molar. And then you will again notice this is also aqueous. So means that we are going to put comma MnO4 negative aqueous X molar. And then we will going to draw the salt bridge. So again, in this case also there is aqueous solution. So the solution must always immerse, there is a metal always immerse into the solution. So in this case also similar with question A, it will be the platinum. So we will put it at the left hand side and then face boundary, because just now we mentioned that normally at the both left and right hand side exactly next to the salt bridge will be the solution. So and then here will be AU3 plus aqueous X molar, and then immerse the AU also immerse in the solution. So this is the cell diagram for equation B.